Yes.
Hello, everybody, and welcome back. If you're watching this on the schedule, it is Tuesday, April 5th, so happy Tuesday. Again, we have a lovely special guest with us today. Miss Vampus is here.
Hey guys, good morning, or whenever you're watching this. I'm actually really surprised, Miss Scanlon, that you didn't say your usual good morning greeting.
I haven't been doing it on these videos because I don't want to scare people who aren't our kids.
You know what? I'm starting to miss that, even though it was so jarring every morning. Anyway, it's good to be back, guys, and today we're going to be talking about factors affecting rates of reaction. And at this point, you should have, if you were following along, listened to or watched the video involving collision theory. Okay, so we're going to go ahead and go into factors affecting rates of reaction.
So, again, yesterday we talked about what makes a reaction happen, so today we're going to talk about how we can speed it up. So, literally, let's speed this up. Just a little quick background info. There are 6 factors that we're going to talk about today that can speed up the reaction. And again, when we're speeding up these reactions, we're speeding up and making more effective collisions. So yesterday we talked about what an effective collision is. Today we're going to talk about how we can make more of those collisions.
Exactly. And just a brief reminder, if you missed out on yesterday's or just chemistry in general, a chemical reaction involves reactants and products, okay? And we're going to talk about how these products are formed and what speeds these reactions up.
Okay, so one of the first things that affects a reaction is the type of reactant you have. So again, you have a reactant, chemistry stuff happens, you produce your products. So ionic substances, they can react the fastest because it's just that attraction between the positive and negative ions, and then they dissociate and dissolve. So we have that silver nitrate as an example. Silver is your positive ion, which we call a cation ion because it's positive. And then you have that nitrate, which is your negative ion, which we call an anion. And anions look like onions. Onions make you cry. Crying is negative. Ha 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 ha.
I love that little review. Oh my gosh, this brings me back to September, right?
Definitely.
Seems so long ago. Anyway. And then moving along, we have covalent substances. They react slower, okay, because it requires more energy and time to break these bonds. So take a look at the example listed over here. Okay, we have hydrogen reacting with iodine. Okay, and that is a example of how covalent substances react slower.
Just a quick review. Remember, ionic compounds are a metal and a nonmetal, and covalent is 2 or more nonmetals. So, great review.
Great review.
Next topic is concentration. So, essentially, this is when we talk. Remember when we talked about solubility factors and how we can speed up how much stuff dissolves? A lot of these things come back into play. So, the first thing is concentration, and concentration essentially is talking about the amount of stuff.
Mm-hmm.
So if we're talking about collisions, you want more stuff to have more collisions. So if you're in a classroom with like 5 people and we say, okay, cool, go run around in a circle, you might bump into people, you might not. But if you have my class, Miss Monatis' class, Mr. Boyley's class, Miss Cora's class, Miss Pearlie's class, Miss Gia's class, everyone comes in together into one room, and we're like, okay, now run around in a circle. There's a bunch more people, and everyone's going to be colliding a lot more. The more collisions, the faster the reaction. So, increased concentration, you're increasing that reaction rate.
So basically, what you're saying is that the more stuff that there is in a given space, there's going to be more bumping into each other, or in other words, more collisions. Okay, so in the diagram that we've provided for you on the PowerPoint, it shows that on the left-hand side, there are fewer particles than compared to the right-hand it just makes sense. And the example that Ms. Scanlon provided, yeah, makes sense. There's more people in a room, there's going to be more bumping into each other.
That is not maintaining a social distance.
Nope. We should be far, far away from each other right now. No collisions.
Okay.
All right, ready for the next factor. Okay.
Next.
So now the next factor is temperature. Okay, and when there's an increase in temperature, there's an increase in the reaction rate. Okay, the speed of reaction is faster. This increases the number of effective collisions, and that makes sense, yes?
So remember how we talked about temperature being average kinetic energy, and kinetic energy is the energy of motion. So if you're moving faster, you have a higher temperature and you're colliding with each other more. So the example we have on the bottom of the slide is, think of if you're driving or have been in a car going 5 miles an hour and you bump into another car. Well, you're not going very fast. The collision isn't going to be very, very bad. But if you are driving at 50 miles an hour and you crash into somebody, the collision is a lot more effective and you do a lot more damage. In terms of people driving, bad crashes are bad. But in terms of chemistry, the harder the crash, the better it is for the reaction moving forward. Okay. Next is pressure. And pressure only affects the gases. So if you increase the pressure, you're increasing the rate of reaction because you're increasing this number of effective collisions. Think of air in a balloon. If you tie off a balloon, you have a set amount of air in it, but if you squeeze that balloon, you increase the pressure in it, and the molecules have less space to move, and they're going to bump into each other more. So therefore, the more bumping into each other, the faster the reaction goes.
Right, that makes sense. All right, moving ahead, we're going to talk about the surface area and how that affects reaction rates. So when there's an increased surface area, that increases the reaction rate. Okay, and why is this the case? It's because the more exposure of, like, the more exposed particles that can react, okay, the more effective the collisions. All right, so if the particle is exposed, it has a larger surface area, the chances of it colliding, okay, is greater. That kind of makes sense too.
So if we have a block of a substance or a powder of it, a 5-gram block of a substance or 5 grams of powder of that same substance, the powder has more surface area, so will react faster. The block has less surface area and is slower. So they like to ask you about powdered substances versus a block of substances. And we'll go through practice questions later.
I mean, just to give you a visual, if you have a block of sugar and you want to, dissolve that, you would want to crush that up to have it dissolve faster. Okay, just a little visual. Okay, let's move ahead.
Next is a catalyst. And again, when we talked about potential energy diagrams, we talked about this. It increases the speed of the reaction because it changes that activation energy. It lowers that activation energy, meaning it doesn't need as much energy to go up to that peak.
Right.
Now, one thing to point out, it is not used in the chemical reaction. So when we say it's not consumed, it's there at the beginning, it's there at the end. It's just kind of a helping hand to guide the reaction to make sure it happens. It's like if we told you to read 5 chapters in the textbook and learn the material yourself, that would take you some time. But if we handheld you and walked you through the material, you would learn it faster. So that's essentially what a catalyst does. We are catalysts in your learning, and catalysts exist in chemical reactions.
Right, and it speeds things up in their reaction rates. Oh, I like that analogy.
I like that too. I just came up with it.
That's really nice. I like it.
Okay, so there is a quick video we want to show you within a video within a video. Look at that.
Wow. All right, let's hit it.
So let's watch it and then we'll talk about it. Ooh. Ah. So
Whoa.
if we back up a second, the green stuff in the graduated cylinder, it's reacting, but it's reacting very, very, very slow because you can kind of see bubbles forming. But as soon as that white powder goes in, and that's an iodine solution, it speeds up the reaction so much it explodes out of the tube. This is the elephant toothpaste demo. If you watch any scientist on any late night talk show, they always do this demo because it's easy and cool and honestly something you can kind of do at home if you have you can do it with home supplies. So
Yeah,
if your
I mean,
family's okay with it,
yeah.
you can try this kind of safely.
I don't know if you guys know, but I was telling Miss Scanlon this, but I don't know if you guys watch Ryan's World. He's that kid who reviews all these toys online, and he's like a billionaire now. Anyway, he was doing this the other day with his mom, and it's like he was like playing a scientist and stuff. It's super cool. It was really cute. But here we're showing you, okay, the formula, and that the emphasis we want to point out is the iodine. Okay, that's the catalyst right here in this equation, that this is what is making it happen much faster, and this is why you have the visualization of this elephant toothpaste, and it's because of this catalyst. But we also want to emphasize that, look at the iodine. It starts in the reaction, right? And then it also ends untouched in the products, okay?
So the whole mechanism of this reaction you don't really need to be familiar with, just that catalysts aren't consumed in the reaction.
That's right.
Now, one thing you are responsible for, if we give you this reaction, and we ask you if it's endothermic or exothermic, you should be able to tell us that. So if you have heat as a product, again, it's after the arrow, that means it is going to be released, and that means it is exothermic.
Right. So this is the point that we want to point out. Key points. Exothermic reactions, heat is released, and if you're looking at the chemical equation, the heat is going to be in the product's side. Okay, that indicates that heat is released and it is exothermic. Okay, so from this slide, we want you to take away two things: that catalysts are not consumed in a reaction. All right. So it starts in the reactants and it also ends in the products, not consumed. And then the other point is that in an exothermic reaction, heat is released, and you'll see heat on the product side of the equation.
Okay. So one of the next documents you have is practice questions. So at this point, pause the video, work on those practice questions, and when you're done, join us back and we're going to go over them with you. Welcome back from doing practice questions. You should have paused it. If you didn't and you're skipping and you're watching it through, well, that was awkward. Anyway, question 1 is talking about, it's honestly a bunch of words and it's a lot to read, but the question itself it's not hard. So if we're just focusing on that very last sentence, and it looks like it's getting cut off a little bit here. Which orientation, so which way the particles are arranged, will make the activated complex. So the question gives you what the activated complex looks like. So out of the answer choices, which arrangement of these particles looks most like the activated complex? And you should be thinking B.
Okay, right. And let's just backtrack a little bit. Okay, some key words that we want you to highlight is orientation. And when we're talking about, when the question asks, what is the orientation? It's asking you the physical, like what it would physically look like in order to produce this activated complex. So you're going to take a look at the key over here. Below the key, there's that like diagram of what this reaction looks like using these molecules. And if you look at the activated complex, which one of these choices is going to give you that configuration? That's basically it. Okay?
Okay. question 2. A chemical reaction occurs when particles, so this is going kind of back into yesterday's lesson about collision theory, and the only thing you needed to pull out of that was, in order for a reaction to happen, these particles need to collide with proper energy and proper orientation. So in the baseball example, that was scoring a home run. And here, this is essentially the one thing about collision theory you need to know. Proper energy, proper orientation. Okay, jumping to question 3. A reaction is most likely to occur when the colliding particles have proper orientation, and if you paid any attention to the last question, it is D, energy. Again, the same type of question will come up over and over and over again. Okay.
Jumping ahead to question number 4, what is required for a chemical reaction to occur? And this is just a reiteration of what we've just said, and the answer should be letter C, effective collisions between reactant particles.
Again, standard temperature and pressure, and that's one condition that we only really care about that in the gas unit. A catalyst, you don't need a catalyst for the reaction to happen. And then equal number of moles in products reactants, no, that's just there to confuse you. Okay. Number 5, it says, as the temperature of a chemical reaction in the gas phase is increased, the rate of the reaction is increased because, so essentially why do reactions speed up? And that is
letter B, guys, because more effective particle collisions occur. And that pretty much sums up what we've been talking about in this entire PowerPoint. Okay? Number 6.
As temperature of a reaction increases, it is expected that the reactant particles collide.
A, more often and with greater force.
Again, if you're increasing that temperature, you are moving faster. And if you're moving faster, you collide harder, and then you collide more frequently.
Mm-hmm.
Number 7 says a 5-gram sample of iron is placed in 100 mils of HCl. What changes result in the fastest rate of reaction? So how can we speed this up? And if you look at the answer choices, we have concentration and surface area being talked about. So if you want to speed up the reaction, what should you do with the surface area? Increase it or decrease it?
So like we talked about, increasing the surface area would definitely increase the reaction rate. Okay, and so therefore, it leads us to answer A, increasing the surface area of iron and increasing the concentration of HCl, hydrochloric acid.
Exactly. Increasing surface area and concentration speeds up reactions.
Mm-hmm.
Okay.
All right, let's move ahead to practice question number 8. At standard STP, which 4-gram zinc sample will react fastest with dilute hydrochloric acid? So this one, you're going to take a look at your choices. Which one is going to give you the fastest reaction rate? And you should have chosen C, powdered. Okay, because why? There's more surface area in a powdered sample of something as opposed to a lump, right? If it's a lump, you would want to break it up to increase the surface area so that the number of collisions or contact can happen more, right? And the other ones, they're all a solid thing. So this one, C, makes sense. More surface area, more collisions.
Whenever you see powdered, that always gives you the most surface area option.
Right.
Okay. Number 9 says a catalyst increases the rate of reaction of a chemical reaction by talking about, if we look at all the answer choices, C and D are talking about increasing energies. That is not right, either of those. Providing the required heat of reaction. And we said heat of reaction, that's your delta H. That's the heat of the products. minus the heat of the reactants. And if you add a catalyst, those two numbers don't change. But if you have a catalyst, so here is your potential energy diagram that I'm drawing, a catalyst doesn't change where you start, doesn't change where you end, but only creates a different pathway with a lower hump, meaning it is choice A. And lastly, number 10.
Yeah, let's move ahead to question number 10. Given the balance equation representing a reaction. So take a look at the chemical reaction. Which set of reaction conditions produced H2 at the fastest rate? So with this one, you have two things that you want to look at. Okay, if you look at choice A, it says a 1 lump of zinc in 50 mLs of 0.5 HCl at 20 degrees Celsius. So you have to look, so they're asking to look at surface area and also temperature. So what do you know about the factor of surface area? You want to have more surface area to increase the reaction rate. And then you also want a higher temperature, okay, to have an increased reaction rate. So that leaves us with choice D, powdered zinc, and also 30 degrees Celsius.
One other thing to point out is that concentration is also mentioned. So that big M, remember from solutions, that is your molarity. So a 1 molar solution is more concentrated than D. So choice D has the highest surface area, highest concentration, and highest temperature.
Right.
So on that note, that is it for rates of reactions. We hope you've learned valuable information. You've enjoyed our lovely chemistry podcast lesson thing.
Yes, you're making all our podcast dreams come true. All right, guys, hope this was helpful, and we will see you next time. Bye.
Bye.